Hi guys, this is Ms. Martinez, and in this video we are looking at graphing reciprocal functions. I know there's some music going on in the background. I'll tell you why in just a moment. I'm looking for you all to be able to graph reciprocal functions, apply translations to these reciprocal functions, and use reciprocal functions to solve problems. Here's why I have this beautiful music playing in the background. This is a photograph of our very own El Paso Plaza Theater. And it was actually built in September, well, it was opened, I should say, September 12th, 1930. They began building it in the years prior to, and it was a huge undertaking and a remarkable turnout when they opened it up to the public, because it was the only one like this from Dallas to between Dallas and Arizona, and so people came from all over to this theater. It was intended to be a film house, and it's where people came to watch the very early films that were actually in black and white and really quite romantic. It was also set up to be a stage house so that performers could, if they wanted to, perform on that stage. And it's really special and important to me because that's actually where Ariel proposed to me a couple years ago. So that's a picture of that going down, and yeah, it was really romantic. We know someone that actually is on the community foundation that owns it, and that's how we were able to make that happen. You'll have to ask for the whole story later. It's too long to put in this video. But needless to say, you can't really see it in this picture, but here in that lower left-hand corner you can see what looks kind of like a piano, and that is actually a Mighty Wurlitzer organ. It's original to this theater. It was actually the grand gem of this theater when it opened. It cost $60,000, and it is what played the music for the silent films. Theaters had these organs because they needed to be able to have a whole orchestra sound without having to pay for a whole orchestra to come and play. So that was an affordable way to make that happen. And I bring all this up because the way that organs work, air is pushed through a series of pipes, and notes are played, or are the result. And to figure out that note, that frequency, like the ones that you would hear from our organ in the Plaza Theater, it is estimated as a function of the pipe's length, and it is in fact a reciprocal function. So the frequency is found in terms of the length of the pipe, and it is V over 2L, where V is the speed of sound, which is about 3.41 meters per second. So based on the length of the pipe, there will be a different note produced. So let's get started here talking about reciprocal functions. I want to introduce the parent reciprocal function, the most basic of them, and it is f of x equals 1 over x. We're going to find the domain and the range as well as graph it. So let's begin by kind of just creating a table of values here so that we'll be able to plot points and sketch the graph. We're going to go from -4 to 4, and it's going to be really pretty simple here. All you have to do is plug in that x value to your denominator. So that would be -1/4 negative 1/3, negative 1/2, negative 1. You cannot divide by 0. So if you were to plug in 0 into your denominator, the result is an undefined statement. So our graph is undefined at 0. And in just a moment, you're going to see what that means. At 1, oh, that would be a positive 1. And then at 2, it would be 1/2, 1/3 at 3, and at 4, it would be 1/4. And if we plotted these points very carefully, the result would look like this. You're going to have a graph that's really composed of two parts, and they never are going to touch the y-axis or the x-axis. You might ask, well, why is that? Okay, well, 1 over a really, 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 really large number, like let's say 1 over 100. That's fairly large. Well, that's 1/100th. It's still not 0, so it's still not going to cross into that negative area. And as we already saw there at the y-axis, where x is 0, it is undefined. And so as you get closer and closer and closer to your y-axis, those values are just going to get really, really, really large or really, really, really small. This is an interesting scenario, and finding the domain and range is really pretty straightforward here. The domain, it goes to the right and to the left forever, but it is not ever going to be 0. And the same for the range for this parent function. It goes up and down forever, but it never actually touches 0. This interesting shape is called a hyperbola. This reciprocal function graph is called a hyperbola. Not hyperbola. Okay, hyperbola. All right, so let's go. There are more graphs. There are what you could call children of this reciprocal function. They're going to look a lot like the parent, but they're going to be a little bit different, and those differences are called transformations. And the reciprocal functions, they can be of this form where it's a over x minus h plus k. And we're going to see what a, h, and k do to change our graph. The first thing is vertical asymptotes. We saw our vertical asymptote just a moment ago. Vertical asymptotes occur where your function is undefined. And functions are undefined when the denominator is 0. So for our parent, it was at 0 because your denominator would be undefined when x was 0. But here, in this case, if you were adding or subtracting an h value, it's going to change where your vertical asymptote will be. The next thing to discuss are your horizontal asymptotes. And they are going to occur at that k value. That k value essentially moves your hyperbola up or down. And if there is no k value, that means that your k value is 0, and your asymptote will remain like it was with the parent function at y equals 0. The last thing that can occur are stretches, compressions, and reflections. A stretch, well, let me start, with a reflection. Reflections occur across the x-axis when your a values are negative. And we're going to look at an example to clarify what a reflection looks like. If the absolute value of your a value is greater than 1, so something like a 3, a 5, a 7, negative 2, any one of those, it's going to stretch your graph. And conversely, if your absolute value is like a fractional amount, like a 1/3, a 1/2, a 1/5, it's going to compress your graph. So let's look at some examples where this happens. We're going to identify our asymptotes and graph. So let's begin with our vertical asymptote. This occurs where your denominator is equal to 0. So we're going to figure out what would make it undefined. It would be undefined at x equaling 1. So we're going to sketch our vertical asymptote there. Our graph is never going to touch or cross that line. Now the horizontal asymptote, where will that happen? It's going to happen at your k value, which you don't have just an integer added at the end. So that means our k value is 0, and our horizontal asymptote is at y equals 0. Now let's talk about stretches, compressions, and reflections. There are none because our a value is 1, and it is going to have the same kind of structure as the parent. So now to plot our graph, we're going to plug in x values and find where they would be plotted, the y value that corresponds. At 2, if you plug in 2, the output would be 1. If you plugged in 0, the output would be -1. And if you did a few more, this is the structure you would have. All right, so take a moment to get that nice sketch. And it doesn't matter which x values you choose, you just want to pick a few so that you can see very clearly the shape of your graph. All right, let's do another one. Beginning with our vertical asymptotes. They occur where you have an undefined function, which is when your denominator equals 0. So our vertical asymptote is going to be at the line -2, where x is -2, because our graph cannot equal -2. Our horizontal asymptote occurs at our k value, and so the equation of that line is going to be y equals -1. Now stretches, compressions, and reflections. Yes, -3 for our a value, it implies a reflection and a stretch. So if we start plotting some points here, at -2.5, the output would be 5. I just plugged that into my function and did a little math there, and you could check it with your calculator. At -3, the output would be 2. And at -5, the output would be 0. Similarly, at 4, the output is -1.5. At 1, the output is -2. And at -1, the output is -4. And you should see that those dots, they kind of create this nice symmetry, and that is true of these reciprocal functions. The graph, I know it has kind of shifted over a little bit. The graph should look like this when you have sketched and connected those points in a nice hyperbolic shape. Last example here, a word problem that we're going to solve with reciprocals. The junior class is ordering t-shirts from a printing business that charges $45 for a setup and $7.50 per shirt. And what we want to know is how many shirts have to be ordered for the cost to only be $10. Well, we're trying to find the average cost, the cost dividing by the number of shirts. Yes, the whole group, when they go and pay for their shirts, is going to be the cost of all the shirts plus the setup fee, but we want to find the average cost per person. So that would be found by taking the setup fee plus the cost for each shirt divided by the total number of shirts, which is represented with S. And we can write this a little bit more simplified. It would be 45 divided by S plus 750. Now to solve this, we want to know what number of shirts do we have to order, so what is our S value so that our equation equals 10. And then pretty basic math here, we're just going to subtract 7.5 and you can do some cross multiplication here. So that would be 250S equals 45, and that means S is going to be 18. We would need to order 18 shirts for the cost per shirt to only be $10. So that's it, guys. If you had questions, please feel free to write those down and we'll go through them together in class. Thanks.